Welcome to the 1945 Nobel Prize in Physics. This one went to Wolfgang Pauli, not, Rocky's brother-in-law Pauli. No, Wolfgang Pauli, different Pauli altogether. The official wording of the prize was for the discovery of the exclusion principle, also called the Pauli Principle, Pauli exclusion principle sometimes. It depends on where you read it, but the exclusion principle. He received the Nobel after being nominated a number of times, but the final one that got him across that finish line, I think, was Einstein, who wrote in the nomination letter his decisive contribution through his discovery of a new law of nature, the exclusion principle or Pauli principle. Now, the heck was this thing? It basically involves spin theory, which is a fundamental part of the structure of matter. What the heck does all that mean in English? Well, let's take a little look at it. Let's get rid of the scientific gobbledygook and put it in terms that kind of makes sense. It's really not as hard as it sounds. Let's peel back that onion layer. If you remember back from the 1922 Nobel Prize, Niels Bohr developed a model of the atom in which electrons move in fixed orbits around the nucleus. As the Bohr model went into further development, electrons were thought of as having a specific quantum number based on a distinct energy level, how excited they were. And that was all covered in that particular prize. In 1925, when Pauli developed his principle that would ultimately win him the prize, he introduced two new numbers to go along with that original number. The principle states that no two electrons in an atom can have identical sets of quantum numbers. It was much later discovered that that can be said about protons and neutrons as well, but why the heck do we care? I mean, really, what's the point to all that? In many different ways, this shows us a number of phenomena inside the electron cloud of every atom in the periodic table. And this really helps us understand the formation of chemical bonds in between different atoms. Now, it also prevents the electrons, when they're on the atom, from collapsing into the nucleus, which turns out to make them stable, which is a really good thing for us, because if it wasn't for that, all atoms would pretty much form the same sort of thing. Now, as it helped in understanding how atoms form those bonds, it also helped in the creation of the modern periodic table of elements, as well as further proving out exactly what's going on quantum mechanically inside those pesky little structures. Now, let's look at the periodic table and understand for a minute why it's put together the way it is. I mean, why does it have those funky shapes to it? Attempts to build out a periodic table of elements date back centuries. In fact, in the 19th century, it's pretty well known that a Russian chemist named Dmitry Mendeleev made what is thought to be the first real attempt at grouping elements by atomic weight. Only about 60 were known at the time, so there's been a lot of progress made since then. In fact, Mendeleev even realized that when the elements are organized by weight, certain types of elements sort of occur in regular intervals or periods. Well, now we've got them organized in a way that you see here that kind of looks like this really bizarre shape. Well, that's mostly been done since Mendeleev's time, but we owe a lot of the definitive pattern here to the Pauli exclusion principle and information that came out of that. Today, about 118 elements are known, and the Pauli exclusion principle does help us get it in exactly the right places and fill in a bunch of other information. And these groups all have different characteristics, and if you Google it, you can find out everything about every group you want to know. But let's just take group 1 as an example. That's that first column on the left. It's all highly reactive. In fact, hydrogen is the most volatile element in the universe. If you doubt that, Google what happens when hydrogen meets a flame. All of them, with the exception of H, tend to be very shiny and soft. So that entire row, you see how there's a little bit difference in color in this picture in that column. That entire column is characterized by that same highly reactive characteristic. Now, the ones that are in different colors than hydrogen, which fall, in the second row and down, all tend to be very shiny, but they will also, if you put them in water, will do anything from burst into flame to explode. So be really careful when you deal with these things. And those different columns really do give you a lot of information about what would happen in a chemical reaction. Now, this prize could have very easily been in chemistry, but the same kind of general, hey, this guy did a lot for us kind of thing applies when it comes to Pauli. So yeah, there's a lot of applications to chemistry. This is subatomic physics at this point. So was it a chemistry prize or a physics prize? The Nobel Committee gave it to him in physics, and that's what he was nominated for because he also had a list of other accomplishments in the field of physics. And I think this was just sort of one of those, hey, he's going to win it anyway. Let's just give it to him for the thing he's best known for. But one of the other things he did that really stands out was he was the first to postulate about this thing called the neutrino. He did it in about 1930. The neutrino wasn't discovered until much, much, much later. So he was one of those guys that really understood the subatomic world. And a lot of his work really had direct application in quantum mechanics. And the Pauli exclusion principle helped explain quantum mechanics very well. It just also happened to have applications in chemistry. So, he did it through the physics lens, but it just happened to apply elsewhere. So that's why he got the prize in physics. So while he's definitely a fundamental scientist, he's a guy who really did help us unlock some of those secrets of the subatomic world. I think, was he chemist? Was he physicist? I think at that some of those levels, the lines get kind of fuzzy. But because he came at it from the physics perspective, they're definitely worthy of the prize. Now, we're going to dive into some more modern ones. They're coming up. There's a lot of great stuff left in the physics prize list before we flip over and start doing the chemistry prizes. Don't forget to click subscribe and click that like button. It really does help us out with the algorithms. Everybody, see you on the next video.